All right. Welcome everybody joining us on YouTube. I'm really excited to present our main speaker for today's Illustrating Math seminar online, who is Chaim Goodman-Strauss, who is currently the outreach mathematician for the National Museum of Mathematics, or MoMath, in New York City. Chaim has a long history of illustrating math, including work in the geometry labs of the University of Minnesota and as co-author of the book, The Symmetry of Things. And he's also well known for his work in aperiodic tilings, which notably includes being part of the team among the recent team to discover the aperiodic monotile known as the hat and its variants. So I'm very excited to hear from Chaim today. I will pass the mic over and we can get started.
Thank you very, very much for having me. And let me just start by sharing my opening screen. So I guess the first thing I would like to say is here it's the year 2023, I believe. And it's really just amazing that this community exists. I mean, I was reflecting this morning about what my sort of early life was like in this, doing mathematical illustration. I was remembering that when I was 15, programming my very first computer illustration of just a helix and sort of tilted to the screen on a 32K memory computer, and trying to at the same time build the geodesic domes in the backyard out of rolled up newspaper. And there really wasn't anything. I mean, really the truth is, for me, the only real contact I had with anything was MC Escher, basically. And I think a lot of people my age had that, or maybe nothing at all. I mean, it's really just astounding now that there's this real rich and robust community and we're all in touch. It's just kind of really kind of moving, frankly. So I've been involved in illustration. My abstract might have seemed a little bit, I was saying I've been doing illustration forever. I think basically all of us agree. I mean, it's probably my abstract applies to everybody here. I've been involved with illustrating stuff ever since I've been learning mathematics, just because it's how I understand mathematics. And I'm sure that's the same for many of you. So these are some notebooks from my early days. And I was just remembering too, how old was I when I first had a tool that was better than compass and straight edge and a Xerox machine? I used the Xerox machine for these kinds of fractal things, not here, but you can see that was a very useful thing. I was 25 years old. I was 25 years old before I had a more effective method of drawing than just simply doing it this way. And I think that really says a lot. I mean, that was basically my formative years. I was spent making these sorts of things. This was the only way to really render stuff. This here is a particular structure that I'll talk quite a bit about. I was obsessed with it from the time I was about 20. Here you can see it's a piece of a stellated dodecahedron with stellated dodecahedron on the points. And I guess I can share this. I'll share this here because you guys, this is a safe place. But right around the time I made this, I also made an image I'll show you some further images, more modern images of the same structure, but I made it on a Xerox machine, taking little dodecahedrons, Xeroxing them and pasting them down and Xeroxing that in this kind of fractal fashion. And I gave it to my future wife as a love gift, and she accepted it. So that she appreciates me for who I am. I think, that's just because it's a safe place. I think we can all relate to things like that. So this is how I learned hyperbolic geometry. I really did. I learned hyperbolic geometry by doing compass and straight edge constructions in the hyperbolic plane. So this is a compass and straight edge construction of the 642 triangle tiling. And you can kind of, in this image, maybe see this outline of web tracery on the outside that describes the construction. And there's a whole history there. I also learned hyperbolic geometry by doing just combinatorially, like just drawing, graphs and trying to figure it out. The tools just simply did not exist. And so this amazing work in VR, not just hyperbolic stuff that we just seen, but also now the new stuff in various other spaces, the 3-sphere, of course, but also S2 cross S1 or SOLID and so places. This is what I was trying to do in 1990, is just imagine living there, just try to dream it. And so I have pictures of Saul and other places. But here, this is sort of the best. This on the right is the guy who ran for governor of Texas in 1992. Actually, that's I've forgotten his name, Clayton Williams. So then on the left is the view of what you would see. And I think many of you are probably familiar with this. If you were a transparent head on a sphere and you were looking in the geodesics, the light rays were going around and around the sphere. When you look straight ahead, you would first see the back of your head in any direction. And then if your head was transparent, then you would continue to see on. And so there's all kinds of funny things here, like the way the ears work is very strange. Here's an upright ear, and there would be a backwards ear in that direction. And around the same time, I was also doing stuff like this. So this is, you may be familiar with the 59 icosahedra. Here's 58 of the 59 icosahedra in a single small box, which I was very pleased with. If you know what they are, then you understand how this might be possible. It's the stellations. What it means in this context to stellate a polyhedron is to chop up space by its spatial planes and then select out bits. And so here's space chopped up by the spatial planes of an icosahedron. And then around the same time, I was doing a lot of these kinds of cartoony drawings. So I grew up in the kind of a hippie part of Austin. And so I was very exposed to underground comics as a kid, for better or worse. And so I was doing handouts in this style at the time. And then I was also making quite a bit of math fun. So for the subsequent 30 years, this has been really one of my major, I would say, in some sense, I would view this maybe as one of my main artistic practices, is not just the illustrative aspect of this kind of work, but also the social or participatory or kind of participation art aspect of these kinds of materials. So math fun is something that I really actually take pretty seriously. And so on the left, in the image here, a few samples of things that all kinds of stuff. I'll talk a little bit about some of them, but you can see this hand-drawn Infinity #1, which was a comic from, or not exactly a comic, but it was from 1994. And so it had all these kinds of, this is right when I was first using Adobe Illustrator. You can tell this mix of hand-drawn and Adobe Illustrator. This is all paste stuff. So I would take the Adobe Illustrator, type what I wanted, print it out, and then glue it down to a piece of paper with whiteout and write all over it. And then right around then is when I was first, this is the very first stuff that I was able to do in any other way besides hand. This is this exact moment. And so I'll talk a little bit about this. This is a stickers. These are stickers. In fact, this is the workflow I use today. This is the same workflow I've used now for over 30 years. So this was, and this was a real important moment in my life. So this is a combination of Mathematica and Adobe Illustrator, and then printing it out, in PostScript. So anybody that's old enough to know, it didn't used to be possible to do this sort of thing at all. So these are math stickers for enhanced living, and these are some of my first forays into mathematical programming, as well as having fun with Adobe Illustrator. And so in this Infinity #1, it came with a sticker. It also came with some polyhedra. So this is something that has also been a multi-decade project. Is some of these really date from this period of time. I guess you can't quite see it. I guess I can't quite zoom in. I didn't really structure this right. But if you go to this, take a quick screenshot and go to this website, and I hope you all will. This has an archive of approximately, I don't know, I don't have any idea, scores of different kinds of polyhedra patterns to download and to put together. And many of them I have been using all this time with kids. And the point of these is that they're decorative, sure. Oh, so here's some kids. That's what they look like when they're having fun. So the point is that they're decorative, sure, but they all have this kind of pedagogical quality to them as well. So there's this surface decoration, but what I really was thinking in this case was to look at the sort of a fractal octet truss. It's the same exact structure that I showed you I showed you some polyhedra earlier that had a similar nature. If you imagine that this is made out of blue jello or something with black nuggets, the jello is tetrahedral and the black chunks, it's not a surface decoration. Those are solid black octahedra inside of the model. And I don't have the other photograph, but if you look at the lower left, you can see two tetrahedra. One of them is the one I just showed you, and the other one isn't. And again, I'm sorry, I don't have a photo, but here the tetrahedra are getting smaller towards the top. In the companion model, the tetrahedra gets smaller towards the bottom. So remember, this was in this thing that was being distributed to kids, and there's the tetrahedra right there. And so what I was always interested in doing with Math Fun was to try to overlay as many different kinds of as many different ways to appreciate this as possible. So there's the actual thing, which is just kind of fun and goofy, and you can color it and so on. But then there's these models to make if you're a bit more invested. But then on top of that, there's actually some real mathematical illustration going on. The actual nature of these fractal octet trusses, which I don't know if any kid ever got that out of this, but it was always there, and it's always been a part of what I've been doing. So all of these patterns have a genuine pedagogical meaning. And again, I hope you will go take a look at that. So here's one of my favorites. This is a very simple model, and it's a very familiar geometry to people, I think, but I think I'm honestly really personally very proud of this. I've got all sorts of things I could be proud of, but I'm really, I suppose, but I really like this one. And it's just a very simple thing. It's just an icosahedron with 4 tetrahedra stuck on it, but it illustrates, of course, that the icosahedral symmetry, the tetrahedral group, the tetrahedral symmetries are a subgroup of the icosahedral symmetries. And this is exactly what, if you have a compound of 5 tetrahedra and you take the intersection of all of them, then you would have this little icosahedron in the middle. So that's the point of that model. And again, this is meant for kids. I mean, I suppose probably thousands of these have been made now by children. This is meant to be made in under an hour with cheap materials, easily reproduced, accessible, and then this one probably never got made. This is just a quick snapshot. There's a tremendous number of purely pedantic models, such as the truncated octahedras filling space. So there's just tons and tons of this sort of stuff. This one's kind of beaten up, but that's all in that same series. And this kind of thing is again in that mode. So this is the whole point. Is not that I'm showing you a compound of an icosahedron. I mean, what is that? What is that? It's a snub cube, actually. That's cool. So it's actually not that I'm showing you a compound of a snub cube and its dual, but rather that this is part of this whole practice of getting kids to do this out there in the world. Okay, so this is back to this guy. This is that dodecafoam again. And so in that same mode, here again is one of these polyhedra that I was just showing you for kids. Here it is, the same structure I was struggling with all these years. Here's, you can imagine these are black dodecahedra stuck into this thing in some sort of fractal manner. And here it is yet again in another rendition. It's the same stuff now where we have blocks of this stuff where you can imagine this is like some sort of pink aspic with dark purple dodecahedra stuck into it. Every one of those pentagons has a dodecahedron underneath it, and they're all fitting together very nicely in this structure. This is the thing that I offered my future wife back in the day. And so over a period of time, eventually I did get a hold of some computers. I guess this is when I was at the Geometry Center back in not 25 years ago. I still have not 3D printed this because of just inertia or something, but also because my hope would be to actually feel this tactily in some sort of tactile fashion. And I haven't really, I just haven't gotten around to it, but it doesn't seem like maybe the resolution would be where my imagination would rather be. So around the same time, these are some more math fun from 2000 when right when I got tenure, I guess. I produced these very rapidly. And these are trading cards from the Ptolemy Math Card Company, which is the world's largest and most prestigious, I might add, the world's largest fictional mathematical trading card company, at least to date. I'm sure somebody might usurp that. But so the Ptolemy math cards have these fronts, and here again is yet another image of the dodecafoam. So there's dodecafoam again. If you look at the cards, you can see 3 of them spelled Dod, Ekaf, foam. And these are different things in distillation. And then on the back, they have a little bit of information, and then including information about the company. So this one says the Ptolemy Math Card Company was founded by Tibetan monks. That's pretty fascinating. And since 1911, all the dates were different. And then just another kind of bit of math fun. I was surprised that, so the University of Arkansas, like all major sports-oriented schools, protects its mascot very vigorously. But for some reason, the people that controlled the logo kind of didn't mind this and kind of got into it, which sort of really surprised me because, they could have been assholes, frankly. So I guess one thing, that's sort of like one direction. Another sort of thing I would like to talk about.
Sorry to interrupt. I got a hand raise from
do.
Bathsheba, and I wanted to give her a chance.
Bathsheba, hello, Bathsheba. Yeah. So.
Oh, hello.
Hi, how are you? It's so nice to hear from you.
All right, I wasn't expecting to speak.
Sorry, I didn't know if you had a question, so I figured I would respond to the
Oh, okay. All right. Well, anyway.
All right.
Okay, so moving on. So I mean, I may end up finishing early. I've just put in tons and tons of stuff, and I'm either going to have like twice as much stuff as I need or half as much. I'm not really sure. We'll find out. But this is just sort of the end of this math fun segment. I guess one thing that I wanted to say is that always, I think like many people here, I use mathematical illustration as a fundamental part of my mathematical research. To me, they're not really separable in the sense that I feel like I can't understand something until I can kind of apprehend it, and apprehending it in the literal sense. I guess actually there's multiple literal senses, right? We say apprehend to catch something, but also to understand it and see it. So, and this is right after this here is a illustration from my thesis that happens. This is my very first sort of adventures into Adobe Illustrator. We're also kind of doing this kind of technical illustration. But on the right is a Fimo model of basically not quite the same thing, but it's a much simpler version, much simpler structure in the same general direction. And so making things out of Fimo was really important too. I should have kept it in, but actually my thesis was really actually was an infinite collection of magic tricks in effect. And so what's not shown here, unless I left it in, I did not. What I should have left in is, that was very important to me as well. I mean, I didn't have any choice about it. I just got the thesis I got, but it was really cool that I felt that I could actually render it all as like actual rope tricks. So I actually have some photographs of rope that renders whatever this is about. So this is one of the things that I was interested in quite a lot, and have spent most of my mathematical career, trying to understand are these so-called aperiodic sets of tiles. And this is an illustration from pretty much right after I got a hold of a computer of my own for work, after I became a professor. This is, I just think it looks cool, awesome. Really, that's the truth of the matter. It's deliberately evocative. It's meant to be evocative of certain traditional designs that are based on on this kind of octahedral star-shaped thing and the cross. You can find this cross and octahedral star-shaped thing motif it's very common. And but here, of course, these aren't octagons. They're these weird little dimpled things, and the void is the same shape as the thing that's next to it. And so what do we really have here are two different kinds of shapes. We have this shape, which is also filled in some of the time, and we have this cross shape. And one of the things that okay, so that's actually an aperiodic pair of tiles. I didn't draw one of them, but it's an aperiodic pair of tiles. And until recently, it was tied for simplest known, actually. And so the process of drawing something like that was very important to me to actually understand. I couldn't have done the work without that. I'm also really pleased that a lot of the illustrations that are out on Wikipedia and so forth seem to be derived from my papers. which is pretty cool. So they're often redrawn. So like, for example, this illustration isn't on Wikipedia, but somebody took this one and drew it more to their satisfaction, which I think is great. And so I won't get into that. And so this is more technical work. Just these are the kinds of illustrations that are in my work normally. This is from my, I guess my big paper was that given any one of these hierarchical substitution structures, there's a way to cook up matching rules that then force that structure to emerge. So on the bottom, we have the Sphinx tile, and the Sphinx tile is a reptile that can form larger copies of themselves, and you can do that ad infinitum. And then these crazy marked tiles can only form, the markings ensure that they can only form these sphinxes in these larger hierarchical things. So I suppose that's my mathematical claim to fame, such as it is. But just because it's sort of a safe place in certain sense, this is the secret of what I was really doing in the back of my mind. These illustrations never made it into anything like a publication, but this is the kind of nonsense I was really drawing for myself to understand sort of abstractly what was going on with the routing and signaling and so forth. And then these are sort of just, this is just sort of a random slide out of another talk just to show you more of this kind of stuff. This is actually a collection of 25,000 different aperiodic sets of tiles, which I really liked. So I'm also advertising that because maybe some people here would like that kind of thing. So, you know, there are only a few dozen, maybe, except now I have 25,000 of them. So my mathematical work is really along these lines, is to largely, lots of it has been to involved with, again, working with shapes that then, tiles that then can only form these particular kinds of hierarchical structures. In this particular case, I guess I could tell you the result. Looks like I got the time. So you have, part of it is that you have, if you have these collection of tiles here, you can include or not include some of them, and you can have different, and then have sets of aperiodic sets of tiles that allow or disallow various kinds of structures. So for example, if I use the ones that are shaded here, up here, then I would have a collection of tiles that can only form structures of this kind. And if I use the tiles in this one, which is this collection of tiles, it can only form them where you can't quite see, but there's a 2x1 rectangle here, 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 here. It's just the same as that picture in a notation. It's 2 like this and 2 like that, and so on. So again, illustration is how I understand it. I don't really work. That's how I work. I mean, I think like many people here, when I'm writing a paper or working, most of my work is in some sort of weird visual language that I can't explain. And that a lot of the process is somehow translating that into some words that other people can understand. I just want to show you this. This is kind of gratuitous. Well, no, it isn't. It's mathematical illustration. It's a cool mathematical illustration. So one of the things that I was very, very interested in, this is again a slide from somewhere else, is that is self-assembly of tiles, like rules for self-assembly. The reason that this comes up is that quasi-crystals, which are real physical materials for which Daniel Shechtman won the Nobel Prize, have the same apparent X-ray diffraction structure as Penrose tiles. And yet, so the question is, how can atoms do this? And they can't, actually, but there are ways around this. So this is just another illustration of something. This is like, part of my problem is this is like 6 months of work and it's totally unpublished because I just didn't know what to do with it. I need to finish it. But it's also sort of strange and marginal area to work in. So this is another thing, just another illustration. This is a 28 by 7 foot window that's at the University of Arkansas. Okay, goes on and on. One of the things I wanted to talk about is I do a lot of public participation art. And so Bamboo Palooza, this is from 2005, but I did tons of these, or several of these, where people would come together and then they would make stuff, you know, so designing projects where people could actually show up, they don't know what's going on, and they sort of get some instructions, and then before you know it, they make interesting things. And ideally, they work for all ages. So let me just show you a few of these kinds of work. This is a big weaving structure, woven structure, which I want to develop much better. This sort of looks like crud, but it was huge and quick. Here's some sidewalk stuff. Here's some, oh yeah. So I lived in Fayetteville, Arkansas for 30 years, and I guess I was really well known. I lived on a fairly busy corner, and all this yard art was kind of known around the town. It was very easy to tell people where I lived. Just to say, have you ever seen the corner with all the yard art? The math, and they would say, yeah, of course. So these are more of these woven bamboo stars that are due to Akio Hazume, but I imitated and used his technique. And I did a lot of steel work and so on. Okay, so then these are also these are participation art pieces from the Gathering for Gardner, and I don't have this really set up as to show you the process, but this next series of pieces were all assembled by participants at the gathering for in the space of about an hour and a half. By the way, let me just make a pitch. The Gathering for Gardner is coming up this February, and although it is justifiably known as expensive, there are scholarships available. And if somebody could, I can't quite, somebody might have the email from Katie Lasser. I don't know if anybody has got her special email. In any case, I will try to, it'd be great if you would show up. It's in February, there's money available for people to show up. So this is another piece based on sort of Hilbert's curve that I bought out Home Depot once, but I had to go to 2 different Home Depots, in fact, to find enough of these. And this became a piece where there's another Gathering for Gardner piece, or here's another Gathering for Gardner piece, the gyroid. This was again assembled on site in about an hour. These I should also say were all in collaboration with Eugene Sargent, who's an artist in Fayetteville, Arkansas. This is another piece that we did. So that's already 4 pieces, I think. This is that is also from the Gathering for Gardner. And you can see some of the obsessions that I've had actually in my mathematical, that's not. So here's a little bit more about how that's made. I guess these are just some random slides. I didn't mean to put all these in. So you can see, let me go back. You can see some of my obsessions here in a number of these sculptures. You can see that I was really trying to understand hyperbolic geometry all along. I mean, in this talk, you can see that I was doing it with compass and straight edge. You can't see all these paper models that I've made over the years, but here I was trying to render it into reality with, so this is a tiling of the hyperbolic plane by squares, 3 squares and a pentagon meeting at every vertex. And here we are again with the same thing now made beautiful and large. These are geodesics, and they really are geodesics because steel has to go, you can't bend steel sideways. So it was incredibly gratifying to put on those orange lines and see that they went right where they had to go. Combinatorially, they had to go certain spots, but geometrically, they had to go certain spots. Physically, materially, they had to go somewhere, and it always worked out great as it had to. Okay, so this is what we really did was, we made this paper model literally into that steel sculpture. All right, so then one thing I became interested in a few years ago was this system, another system for making hyperbolic stuff. And it comes like this, and you tape, and then it makes these beautiful things like this. So I think many of you will recognize that this is directly derived from Dana Tamina's hyperbolic crocheted work. I mean, and as it happens, Dana and I and a few other people were at David Henderson's workshop at the same time, learning about Beltrami's method of stitching together horocyclic curves, annuli, to make a piece of the hyperbolic plane. And then Dana turned that into the crochet, and then later I realized that this could be done this way. So the magic is that the strips have, you can see they have a different number of teeth on one side as on the other. So even though they come straight and they're easy to, they can be manufactured very efficiently with very little waste. And yet, but on the other hand, unlike steel or paper, they can bend in the plane of the strip. And so they can only form strips of the same turning radius. And so since you have all these strips of the same turning radius and the same width, then this is what they're forced to do by the by the mathematics. It just not necessarily this particular exact shape. They're flexible and strange, but something with constant negative curvature. And that's another application. And that's another application. And you can see here another sort of curvature experiment, making spheres. That's just another public participation art thing. More public participation art. Obviously, the hat tile has been a great source of fun. So I did the Math Factor. This was a podcast I had for about 8 years. Well, you can see down here, 2005 to 2012. So in the podcast 0.5 era, but that was a really great source of all kinds of mathematical and collaboration. Naturally, I do all kinds of, I take a lot of care with my teaching materials. So here's a tip. Here's one that I like from the halting problem. And here's one that's in collaboration with Eugene on make a genuine sphere guaranteed. So I'm still producing math fun and still very interested in math fun. And that led to the 2001 21 Rosenthal Prize, which I encourage you to enter. So if you will take a screenshot of this, you will see that little QR code, and you too can win 25,000 cool dollars. So it's really great. So what I was seeking out here was the money, sure, but really what I was interested in was expounding upon this idea of the orbifold from the symmetries of things. I don't think I have the time to show you this little video that I've set up, but basically the idea is that you can see that this pattern, this particular patterns with this particular kind of symmetry are associated with an underlying surface. In this case, it looks like a little envelope. On the other hand, cutting open the envelope, you get a particular shape that then is guaranteed to tile with that particular symmetry. Here's a little video. I'm not going to show it to you, I don't think. And anyways, so, but that's, I guess the point about this is that this is the orbifold idea is a very technical, advanced, I suppose, idea. But here, how can you reach for and describe it in a way, throw away so much baggage? We're not talking about, group actions on geometric spaces and stuff like that, but throw away what can you get down to so that you can get a bunch of 8-year-olds to do it and actually appreciate and understand the point. And in fact, I can even very frequently, I can get an 8-year-old to explain it to me perfectly from scratch. That's, I think, a huge challenge and a great difficulty, and very important to try for all of us. Anyway, here's some more teaching materials. I just wanted to show you these because I like drawing cute animals. Here, the game is this graph can you two-color this graph is what it really is. If you could two-color it, you could put the fish that are connected don't like each other. And if you could two-color it, you put the fish in two tanks. And unfortunately, you can't two-color it. It's these two guys are fighting. If these two could get along, you can see that they look kind of shocked. They don't even know why they're arguing. They're arguing because I made them argue. I made them fight. I made them fight to make the puzzle bad. Isn't that awful of me? And so I can have conversations like that with the kids. But this is obviously very effective teaching. And then, of course, I want to pitch the symmetries of things. So I should say to this community, to people here, I would like to explain what is going to happen, because I have it's kind of personal. So, of course, we know that Conway is no longer with us, and yet we were always talking about a second edition of the book. And so, but then there was also this whole thing that the book really is, those of you familiar with it, it has this first part, which is kind of explains the general gist of things, and then it just kind of takes off. And the story really is true, that what we did was we wrote the first part of the book, or the first plan was to write the first part of the book for a general audience. And then we decided to do the color symmetries, and then all hell broke. I mean, you can't just stop there. So then the book is suddenly now 400 pages long. So the plan with the new edition, which I think is a good one, is that we're going to write, it was just overwhelming to try to do a full new edition. So we're just going to release a book that is the first part of the original book, that just explains why the magic theorem is true, and for a much more general audience and for much cheaper too. So Symmetries of Things was full of weird stuff. Here's a couple of pages from the new book. So one thing that's happened is that there's just a lot more geometric ornament than there used to be. Some of this ornament is new. Two of the things on the left, three of the things on the left are brand new ornament. And on the right, it's also great because in the subsequent years, there's so much more stuff in the community that we can now highlight. Well, in fact, there's Bathsheba and there's Carolyn. And this is somebody named Shi Yingdong, who, if you don't know her yet, you will. She does amazing work. There's John Koski, Dick Esterly, and Henry Siegerman. So I think we got at least 4 or 5 people here on that page alone. And then similarly, more geometric ornament than there was. I'd also like to make a quick pitch for kaleidoscopes. There's a lot of people here that know about kaleidoscopes, but the spherical ones really are a little bit undersold. So this page is going to change, but here's a few images of this spherical kaleidoscopes. And I just want to say a few words. Okay, this is probably my favorite new image from the new edition of the Symmetries of Things. And maybe this one. So I was also really wanting to find a way to illustrate the unity of spherical, Euclidean, and hyperbolic geometry, but not using the kinds of computer tools which are now been available. I wanted to see if we could do this physically. So we have a physical hyperbolic plane made out of woven material. So this is also an illustration from the new book. And so that's coming in 2024. And I think I have a few moments. I just would like to share a couple of other quick things, if I could. So here is, so this here is so the one thing that does not seem to appear in the literature written down yet, and I could never really get it out of Conway exactly what the process was how do you geometrize an orbifold? So if you have an arbitrary symmetry, the idea of the orbifold notation, if you don't know, is that it unifies, there's a lot of things, but among other things, it unifies spherical, Euclidean, and hyperbolic geometry. And in particular, you can type in any kind of symbol you like, as long as it's legit. And I don't know what it's going to do. It actually did it. Look at that. And it'll actually geometrize the space. And that's all fine. But then there's a lot of parameters that you can then change with that. So where that led to was this work with Vladimir Bulatov, where it's basically the same thing, but you can now do things like load up an image. Oh, maybe not that one. You can load up an image, and you can do things like, move this is probably not the right way to show you, but you can move the thing around. This interface isn't so great, but just because this isn't yet, but you can change the parameters as before. So this one just has this, there's a flexibility in these groups. And then Vladimir put in all kinds of other stuff, which I can't take any credit for. This can take a webcam. I can have my own image here. I can do, let's just try that. That's so cool. Let's just try that real quick. So let's do webcam. And there we are. Hello. So that's how that goes. And then we can, oops. But then Vladimir added these wonderful things too. So we can do this in the, there's all kinds of weird manipulations that are possible in various kinds of hyperbolic groups. I think I will just conclude by saying that what I want to do next, I really want to do these next. So these was experimenting with illustrating illustrating the various discrete groups that act on the 3-sphere, not just the polyhedral groups, but all of the groups. And so the idea was to make these tubing sculptures, because tubes naturally conform to circles. And when you stereographically project, circles become circles. But then the next part was then to put LED lights in these that are programmable. And I got so far as none of these, nothing this complicated, but that's a fine place to stop. So thank you very much for your attention.
Thank you so much. I wanted to open the floor to questions. I know there's folks that are posting questions on Discord as well. Frank Ferris asked if the Orbifold Illustrator is publicly available or if we can expect it to be.
The Orbifold Illustrator? Oh, you mean the thing I just showed you?
Yeah.
It is available, honestly. I just don't have I don't know. It actually, there's some version of it that's I guess it's been sitting around for like 4 years, honestly. So I need to, that's pretty bad. I'll tell you what, I'll see. I think there's a link in, put a link in the Discord chat after this if I can, if it exists.
Amazing. I wanted to ask if there were any other questions. I'm also glancing at the Discord, so you could post them there or click the raise your hand button and I would be happy to unmute you. If not, the Discord is going to continue to be there. All of us have access, would be happy to answer questions. I'm sure the speakers would be happy to hear from you there. I wanted to thank again Chaim Goodman-Strauss as well as Hans and Martin for their talks today. And I will hand the floor one more time to Aaron to close us out.
All right. Well, thanks again, everybody, for coming. Thanks, Chaim, for sharing your wonderful portfolio of experiences and illustrations. And thanks to Hans and Martin as well. Please join us again next month, where we will feature Nelson Max, one of the early pioneers of animation, computer animated educational math videos, and some show and ask speakers who I think are yet to be determined. So maybe it'll be you. If you want to sign up, please sign up using the Google form that that Gabe has posted. Okay, thanks once again. We'll turn it over to the Discord and I'll close this channel.
Thank you.